According to NEC Article 310.15, the feeder wire size should be determined based on the overcurrent protection device (OCD) installed at the load end. In this case, that's the 60 amps breaker feeding the motor starter. For 60 amps overcurrent protection device, the minimum feeder wire size required is number 6 American wire gauge (AUG) copper wire. See NEC Table 310.16. The wiring between the 150 amps main panel breaker and the 60 amps breaker feeding the motor starter does not have to be sized for 150 amps. It can be sized for the required 60 amps load. This is because the 150 amps main panel breaker is not protecting the feeder wire between the two breakers. The 60 amps breaker feeding the motor starter provides the necessary overcurrent protection for the wiring. This information can be found in the following NEC sections. Article 310.15 discusses the ampacity of conductors and includes information on how to determine the allowable ampacities of conductors based on various factors such as conductor type, insulation, and insulation conditions. Table 310.16 lists conductor sizes for 600 volts, not more than 3 conductors in a raceway or cable or earth, with an ambient temperature of 30 degrees Celsius, 86 degrees Fahrenheit. In Table 310.16, you will find ampacities for different sizes of conductors with various insulation types, such as copper and aluminum. These ampacities are based on specific conditions and are used to determine the appropriate conductor size for a given load. The table is essential for ensuring that conductors are not overloaded and that they can safely carry the intended current. When using Table 310.16, it is important to consider any applicable directing factors such as ambient temperature adjustments or the number of conductors in a raceway. These factors may reduce the allowable ampacity of the conductors and need to be taken into account to ensure compliance with the NEC. For example, if you have more than 3 current-carrying conductors in a raceway, you may need to apply a directing factor to the ampacity listed in Table 310.16. This directing factor reduces the allowable ampacity of the conductors to prevent overheating and potential damage. Understanding how to use and interpret Table 310.16 is crucial for anyone involved in electrical installations to ensure the safety and reliability of the electrical system. Other factors, such as voltage drop and allowable current carrying capacity, should also be considered when selecting the feeder wire size. Voltage drop refers to the reduction in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, you can increase the size of the conductor or shorten the length of the circuit. The allowable current carrying capacity of a conductor, also known as ampacity, is the maximum amount of current that a conductor can safely carry without exceeding its temperature rating. The ampacity of a conductor depends on factors such as the conductor material, size, insulation type, and installation conditions. The NEC provides tables that list the ampacities of different conductors under various conditions. It is important to select a conductor with an ampacity that is sufficient to handle the expected load. In addition to voltage drop and ampacity, other factors to consider when selecting feeder wire size include the ambient temperature, the presence of harmonics, and the type of load being served. Ambient temperature can affect the ampacity of a conductor, so it is important to select a conductor that is rated for the expected temperature. Harmonics are distortions in the electrical waveform that can increase the current flowing through a conductor. If harmonics are present, it may be necessary to increase the size of the conductor to prevent overheating. The type of load being served can also affect the required feeder wire size. For example, motors and other inductive loads may require larger conductors to handle the inrush current that occurs when they start. It is important to consult with a qualified electrician or refer to the full NEC code for more specific guidance on selecting feeder wire size. A qualified electrician can assess the specific conditions of your installation and recommend the appropriate conductor size. The NEC code provides detailed requirements for electrical installations, including conductor sizing, and it is important to follow these requirements to ensure the safety and reliability of the electrical system. In summary, determining the appropriate feeder wire size involves considering several factors, including the overcurrent protection device, voltage drop, ampacity, ambient temperature, harmonics, and the type of load being served. Consulting with a qualified electrician or referring to the full NEC code is recommended for more specific guidance. When selecting feeder wire, it's crucial to understand the concept of overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current flow, which can cause overheating, damage to equipment, and even fires. The size of the overcurrent protection device is typically based on the ampacity of the conductors it is protecting. The ampacity of a conductor is the maximum amount of current that the conductor can safely carry without exceeding its temperature rating. The NEC provides tables that list the ampacities of different conductors under various conditions. When selecting an overcurrent protection device, it is important to choose a device that is rated to protect the conductors in the circuit. The overcurrent protection device should have a trip rating that is no higher than the ampacity of the conductors. If the overcurrent protection device is too large, it may not trip quickly enough to protect the conductors from damage. In addition to protecting conductors, overcurrent protection devices also protect equipment and appliances from damage caused by overloads or short circuits. Overloads occur when the current flowing through a circuit exceeds the circuit's rated capacity. Short circuits occur when there is an unintended connection between two conductors in the circuit. Overcurrent protection devices are designed to trip quickly in response to overloads and short circuits, preventing damage to equipment and appliances. There are several different types of overcurrent protection devices, including circuit breakers, fuses, and ground fault circuit interrupters, GFCIs. Circuit breakers are resettable devices that trip when the current flowing through them exceeds their trip rating. Fuses are one-time devices that melt and break the circuit when the current flowing through them exceeds their rated capacity. GFCIs are designed to protect people from electric shock by detecting ground faults and quickly interrupting the circuit. Ground faults occur when there is an unintended connection between a live conductor and ground. When selecting an overcurrent protection device, it is important to consider the specific requirements of the circuit being protected. Factors to consider include the ampacity of the conductors, the type of load being served, and the potential for overloads or short circuits. It is also important to ensure that the overcurrent protection device is properly installed and maintained. Overcurrent protection devices should be installed in accessible locations and should be regularly inspected to ensure that they are functioning properly. In summary, overcurrent protection is an essential safety feature in electrical systems. Overcurrent protection devices protect conductors, equipment, and appliances from damage caused by excessive current flow. When selecting an overcurrent protection device, it is important to consider the specific requirements of the circuit being protected and to ensure that the device is properly installed and maintained. Now let's consider conductor types. Conductors are the materials used to carry electrical current in a circuit. The most common conductor materials are copper and aluminum. Copper is a highly conductive metal that is widely used in electrical wiring. Copper conductors have a high ampacity, meaning they can carry a large amount of current without overheating. Copper is also resistant to corrosion and is relatively easy to work with. Aluminum is another common conductor material. Aluminum conductors are lighter and less expensive than copper conductors. However, aluminum conductors have a lower ampacity than copper conductors, so they must be larger in size to carry the same amount of current. Aluminum is also more susceptible to corrosion than copper, so it is important to use appropriate connectors and terminations to prevent corrosion. There are several different types of conductors available, each with its own unique properties and applications. Some common types of conductors include solid conductors, stranded conductors, and flexible conductors. Solid conductors consist of a single strand of metal. Solid conductors are typically used for residential wiring and other applications where flexibility is not required. Stranded conductors consist of multiple strands of metal twisted together. Stranded conductors are more flexible than solid conductors and are used in applications where flexibility is important, such as appliance cords and extension cords. Flexible conductors are made of very fine strands of metal and are highly flexible. Flexible conductors are used in applications where extreme flexibility is required, such as robotics and medical equipment. When selecting conductors, it is important to consider the specific requirements of the application. Factors to consider include the ampacity of the conductor, the flexibility required, and the environmental conditions. It is also important to ensure that the conductors are properly installed and terminated. Conductors should be installed in accordance with the NEC and should be protected from damage. Connectors and terminations should be properly sized and installed to ensure a secure and reliable connection. In addition to conductor material and type, conductor insulation is also an important consideration. Conductor insulation is the material that surrounds the conductor and provides electrical insulation. The insulation prevents current from flowing outside of the conductor and protects people from electric shock. There are several different types of conductor insulation available, each with its own unique properties and applications. Some common types of conductor insulation include thermoplastic insulation, thermoset insulation, and rubber insulation. Thermoplastic insulation is made from a type of plastic that softens when heated. Thermoplastic insulation is commonly used in residential wiring and other applications where moderate temperature resistance is required. Thermoset insulation is made from a type of plastic that does not soften when heated. Thermoset insulation is used in applications where high temperature resistance is required, such as industrial wiring and appliance wiring. Rubber insulation is made from natural or synthetic rubber. Rubber insulation is highly flexible and is used in applications where extreme flexibility is required, such as portable cords and cables. When selecting conductor insulation, it is important to consider the specific requirements of the application. Factors to consider include the temperature rating, the voltage rating, and the environmental conditions. It is also important to ensure that the conductor insulation is properly installed and protected from damage. In summary, conductors are the materials used to carry electrical current in a circuit. The most common conductor materials are copper and aluminum. There are several different types of conductors available, each with its own unique properties and applications. Conductor insulation is the material that surrounds the conductor and provides electrical insulation. When selecting conductors and conductor insulation, it is important to consider the specific requirements of the application and to ensure that the materials are properly installed and protected from damage. Let's elaborate on the NEC tables. The National Electrical Code (NEC) contains numerous tables that provide essential information for electrical installations. These tables cover a wide range of topics, including conductor ampacities, conduit fill, box fill, and grounding requirements. NEC tables are organized by article number and are located throughout the codebook. To use NEC tables effectively, it is important to understand how they are organized and how to interpret the information they provide. Each table typically has a heading that describes the table's purpose and scope. The table itself is usually organized into rows and columns, with each row representing a specific condition or parameter and each column representing a different value or characteristic. For example, Table 310.16, which we mentioned, provides ampacities for different sizes of conductors based on their insulation type and installation conditions. The rows in this table represent different conductor sizes, and the columns represent different insulation types and ambient temperatures. To find the appropriate ampacity for a given conductor, you would locate the row corresponding to the conductor size and the column corresponding to the insulation type and ambient temperature. The value at the intersection of the row and column represents the ampacity of the conductor under those conditions. It is important to note that NEC tables often contain footnotes that provide additional information or clarification. These footnotes should be carefully reviewed to ensure that the table is being used correctly. In addition to Table 310.16, there are many other important NEC tables that are commonly used in electrical installations. Table 310.15, which we also mentioned, provides adjustment factors for ampacities based on the number of current carrying conductors in a raceway or cable. Table 314.16 provides information on box fill calculations, which are used to determine the maximum number of conductors that can be installed in an electrical box. Table 250.122 provides minimum sizes for equipment grounding conductors. Understanding how to use and interpret NEC tables is essential for anyone involved in electrical installations. These tables provide valuable information that is necessary to ensure the safety and reliability of electrical systems. It is important to consult the NEC code book and to seek guidance from a qualified electrician if you have any questions about how to use NEC tables. Now let's consider ambient temperature correction. Ambient temperature refers to the temperature of the air surrounding electrical conductors and equipment. Ambient temperature can have a significant impact on the ampacity of conductors. As ambient temperature increases, the ampacity of conductors decreases. This is because high temperatures cause conductors to generate more heat, which can lead to overheating and insulation damage. The NEC provides adjustment factors for ampacities based on ambient temperature. These adjustment factors are used to reduce the ampacity of conductors when the ambient temperature exceeds a certain value. The adjustment factors are typically expressed as a percentage of the conductor's ampacity. For example, if a conductor has an ampacity of 100 amps and the ambient temperature adjustment factor is 0.88, the adjusted ampacity of the conductor would be 88 amps. The NEC provides tables that list ambient temperature adjustment factors for different types of conductors and insulation. These tables should be consulted when selecting conductors to ensure that the conductors are properly sized for the expected ambient temperature. In addition to ambient temperature, other factors can also affect the ampacity of conductors. These factors include the number of current carrying conductors in a raceway or cable, the type of insulation, and the presence of harmonics. The NEC provides adjustment factors for these factors as well. When selecting conductors, it is important to consider all of the applicable adjustment factors to ensure that the conductors are properly sized for the expected conditions. Failure to properly account for ambient temperature and other factors can lead to overheating, insulation damage, and even fires. It is always best to consult with a qualified electrician or refer to the NEC code book for more specific guidance on selecting conductors and applying adjustment factors. The NEC is a complex document, and it is important to have a thorough understanding of its requirements before attempting any electrical work. In summary, ambient temperature is an important factor to consider when selecting conductors. Higher ambient temperatures reduce the ampacity of conductors, so it is important to apply appropriate adjustment factors to ensure that the conductors are properly sized. The NEC provides tables that list ambient temperature adjustment factors for different types of conductors and insulation. It is always best to consult with a qualified electrician or refer to the NEC code book for more specific guidance.